Good morning. I'm at a training today. I'm in the building, but I am not able to be in class today. So hopefully this is a good way to teach the class. We're going to start off going over the homework that you had. So in this video, we're going to review a little bit of the homework that was assigned on February 2nd. And so I give you a bunch of time in class, but that was 7, 10, 12, 13, 14, and 16. So we skipped a couple in there. So if you have your homework, please take it out now. We're going to go over it, and please follow along as we go. I'm going to go pretty quick because this is just a review for homework. And if you have any questions, please bring them to me next time. My goal is to go over homework, any other questions you have that the substitute cannot answer next time in class. Alright, so problem 7-10, if a ball is dropped from 160 centimeters and rebounds to 120 centimeters on the first bounce, how high will the ball be on the second bounce? And then it asks on the fifth bounce, and then it asks this generic nth bounce. And so I think this confused a lot of people. Nth just means some unknown number of bounces, and we'll talk about what that looks like. So first things first, if I know that it bounces 160 centimeters the first time, 160 centimeters the first time, then the next time it's going to bounce a percentage of that. So what is the rebound rate? The rebound rate is going to be 120 over 160, and that should be a decimal because it's going down, so it should be less than 1. And if I put 120 divided by 160 into my calculator, I'm going to see that my rebound rate is 0.75. So on the second bounce, I would take 160, and then I know that the 0.75, if I just do this right here, this is the first bounce. And if I multiply it by 0.75 again, that will be my second bounce. And when I put it into my calculator, I'm going to put in 160 times 0.75 times 0.75. And it gets 90 centimeters. Well, if I do it 5 times, the only difference is that this will happen 5 times. The second bounce has 2 of them. So if I'm going to write this next one out the long way and then show us how to simplify it. So it started at 160. It started at 160 centimeters. And then each of those 5 times, it's 75% or 0.75 of the previous bounce. So here I have 1, 2, 3, 4, 5. 75%. It went down 75% of the previous one, and 75% of the previous one, and 75% of the previous one, and it did that 5 times. Well, we have a simpler way of writing this, and this would be 160 times 0.75 to the power of 5, because it repeated that 75 timesing it 5 times. And now, instead of putting in 0.75 100 times into my calculator, all I have to do is put in 160 times 0.75 to the power of, and that's the little up arrow, to the power of 5, and it gives me 37.97 centimeters, and I rounded to the nearest tenth. So you can do that too. Well, if I want to know the 10th bounce, what's the thing that's changing every time? The only thing that changes during the number of bounces is this exponent. So if I want to know the 10th bounce, or the nth bounce, some unknown number of bounces, it's my starting point, which is 160, times the rebound ratio to the power of the number of bounces that happens. And if the number of bounces is 100, that's going to be 100. And if the number of bounces is 20, that's going to be 20. And if the number of bounces is 5, that's going to be 5. So we can create this generic expression for the number of bounces for the nth bounce. This is where exponential functions become incredibly powerful. And this is the crux, I think, of the lesson we did last class. So this is going back to those multiplication and those simplifying using exponential rules, and I'm going to always come back to those relationships between exponents and their rules. So I see that I have two sets of the stuff that's in the parentheses, so I'm actually going to rewrite that out. So I have 3x squared y x to the fourth, and then I have another 3x squared y x to the fourth. And if I expanded that out by saying, oh, there are two x's there, and there are 1, 2, 3, 4 there, and 2 more there, and then there are 4 more there, I could do that all the time, but we have some generic rules. How many x's are there altogether? Well, there's 2, 4, 5, 6, there's 6, 7, 8, 9, 10, 11, 12. There are 12 x's being multiplied. I've got my 3 times 3, which is 9. And how many y's there? There's 1 y there and 1 y there, so y to the second. I'm always going to come back to those generic rules. Now the second one is a little bit trickier because we can simplify before we rewrite it. And I see that I have 3 s's on the bottom and 1 on the top. I could rewrite this, and I'm actually going to do it for us here because I think it's valuable. R times S over R times S, 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 and then T to the third. And before I rewrite it, I'm going to cancel out some things that are the same on the top and the bottom. So when I rewrite this out those 3 times, I won't have to rewrite these two pieces. And we should see that this is R over SST times R over SST, R over SST, and that gets us 3 R's being multiplied, 2, 4, 6 S's being multiplied, and 3 T's being multiplied. So this would be our final answer in its most simplified version. These last two are actually just reminders of polynomial multiplication, and so this is just coming back to this times this. I have to multiply each part, and this is just the rectangle problem, so 3m plus 7 and 2m minus 1, so 14m. We've got 6m times m is m squared. Negative 3m times negative 1 is negative 3m, and 7 times negative is negative 7. And combining like terms, I see that I have the same numbers in those two. So I've got 6m squared, and 14 minus 3 is 11, so plus 11m, and then minus 7. So for that C, part C, we got that polynomial, and it's just a polynomial being multiplied. Now, hopefully, and this is where everybody gets messed up, is that we cannot just distribute, because an exponent means repeated multiplication. And what am I repeatedly multiplying? I'm repeatedly multiplying x minus 3 and repeatedly multiplying it x minus 3. We have to multiply it out. And then I'm going to do my little box method if you need to, or you can FOIL if you like foiling. I got x squared, negative 3x, and positive 9. So we've got x squared minus 6x plus 9. So that's our last equation. But remember, it has to be repeated multiplication. If you said x squared minus 9 or x squared plus 9, then we didn't really honor what an exponent meant. So I told you we'd be going through these quickly. Write and solve an equation for the problem below. If 150 empty water bottles weighed 4.5 pounds, what would you expect 90 water bottles to weigh? So this is actually a pretty simple linear equation. 150 water bottles, and they weigh 4.5 pounds each. That means if I wanted to calculate the number of water bottles that I had, how much does one water bottle weigh? We could do it as a proportional relationship, or we could say, okay, 4.5 pounds for 150 water bottles, LBS from water bottles, is equivalent, well, I can put that in the calculator. 4.5 divided by 150 is 0.03 pounds per 1 water bottle. And then if I wanted to know what 90 would be, it's just a scaled multiplier. So is equivalent to 90 water bottles per how much weight. And so I take 0.03 and multiply it by 90. We know that 2.7 pounds for 90 water bottles. And so this is actually just a linear function, and I wrote a bunch of different equations that are equivalent. I mean, essentially, it's just a big proportions problem. Sketch the shape of the graph for the function y equals b to the x given the following values of b. So we talked about this in class, and it doesn't need to be super complex, but essentially, if b is a number larger than 1, that means, like, for example, that could be y equals 2 to the power of x. 2 is bigger than 1. 2 to the power of x. This is going to be growing, so each time it's going to be growing bigger and bigger and bigger and bigger and bigger. If b is a number between 0 and 1, so let's say like y equals a half. We did this in class the other day. A half to the power of x. We know that the number is going down, so it's going to start maybe really big and then get closer and closer and closer to 0, but never touch, and that would create an asymptote. And if b is equal to 1, it's going to be y equals 1 to the power of x. Well, 1 to the power, let's say 1 to the power of 3 is 1 times 1 times 1. So at 3, we'd get 1. And 1 to the power of 4, 1 times 1 times 1 times 1, oh, that's also 1. And 1 to the power of 0, 1. So we can see that this is going to create this horizontal line at 1 when b is equal to 1. And so these are 3 pretty quick graphs, and you should know what they kind of look like based on the multiplier or the b value. Almost done here. 7-16, write the multiplier for each increase or decrease described below. So if something's increasing by 25%, if I said, oh, that's 0.25 as my multiplier, well, that would actually be a decay because it's between 0 and 1. And so if I want it to be increasing, I need to take 100% of the value, which is 100% as a number, is just the number 1. So if it's an increase of 25 cents, the multiplier is 1.25. If it's decreasing by 18%, well, I had 100%, and I took away 18%. It's not negative 18%. It's 100 minus 18, so 82% is left over. So the multiplier to decrease by 18% is 0.82. We're going to go over those one more time with just some different numbers. Increase, I start with 100% and I'm adding 39%. I have the 100%, so it's increasing. It's taking that 100% of what I currently have and it's increasing it by 39%. So 139% of the previous value, or 1.39 as a multiplier. And if it's decreasing by 94%, it's 100% minus 94%, which I'm left with 6%. That would be 0.06 as a multiplier. So it's going down 94% each time. So that means if I start with $100 and I multiply it by 0.06, I get $6 left, which is a decrease of 94%. So these are a little bit tricky, and we'll need to be really, really sure about why we are 100, and I'll talk about this. This is a great thing to have a question on when I come back. So please appoint yourself to be the person who asked that question. All right, so here we're going to talk about, hopefully you've gone over your homework already, and now we're going to be talking about 7-1.2, that portion of the lesson. So please take out your student workbooks and turn to 7.1.2 in there, and while you're doing that, I'll go over the lesson objectives. So my goal for you today is that you're going to deepen your understanding, extend your understanding of exponential functions by looking at the multiplier, the b value, and the starting point, which we talked about last class, the a value, in different representations. And hopefully by the end of class, you'll be able to generalize the roles of a and b for the equation y equals a times b to the x. Now we talked about this just a little bit the last time we were working together. But I just want to make sure that you are aware of what our objective is. The goal is to get through 720 and 722 during class, and there's going to be a little bit of homework at the end of class. So today you're going to deepen your understanding of exponential functions in a bunch of ways, but just remember something that I wanted to make sure, and we talked about this in the homework portion, that if b is bigger than 1, the equation is growing, and if the b value is smaller than 1, the equation is decaying or going down. So we need to be sure that you have that memorized. There are very few things that I'm going to have you memorize in this class, but the b value will determine whether it's growing or shrinking. So we're going to explore a bunch of different representations today of exponential equations. And when we're working through different problems are actually going to give you different connections between either a table, a graph, an equation, or a situation. So I'm going to outline what those are right now, and I really want you to be paying attention to what those are. So when you're doing problem 7-20A, you're going to be going I'll get my pen out, 7-20A, you're going to be going between a table and an equation. So maybe you're going to start from a table and go to an equation. In 7-20B, you're going to go from an equation to a situation. So 7-20B. So this is all the same problem. So this is 7-20 is quite a big problem. In 7-20C, you're going to be going from a table to a situation. 7-20C. You're going to go between the tables and the situation. And in 7-20D, you're going to go between the situation and the equation. 7-20C. So you're going to be going this way for C, and this way for B. Now these are, I think, some of the three most important pieces. We're going to be talking about that graph piece later on, probably next class or the class after. But these three kind of, the table, the situation, and the equation are the three most relevant pieces to today's activity. All right, so after I read these directions, I'm going to have you pause the video. You're going to need to work on a separate piece of paper because there's definitely not enough room on your piece of paper. And if you need to use a whiteboard, feel free to use a whiteboard. But again, I want you to have these as notes for yourself. Please read the directions. There's a lot of directions to be read. And I want you to spend about 20 to 30 minutes on the first question, 7-20. There are lots of parts to that, and there's lots of conversations that you can have. 7-21 is a review of last class, and 7-23 is pretty straightforward as it relates to just quickly sketching something. Notice that we're not doing 7-22, and your homework tonight is going to be 7-24. So please pause the video now, and near the end of class or at home, you can go onto mrgermanis.org and view the answers on mrgermanis.org. View answers after class at mr.germanis.org. And you can view the videos there. Under the lesson, it's going to be called, February 26th sub plans, and you can watch this video embedded into that. All right, hopefully at this point you have done the activity in class and you're starting the homework, so you're at home and you're viewing these activities. And I'm just going to read these problems out loud. Arnold dropped a ball during the bouncing ball activity and recorded its height in a table. Part of his table is shown at the right. What is what is the rebound ratio for his ball? At what height did he drop the ball? And then write an equation that represents his data. And explain your equation. Okay, so first things first is we need to determine the rebound ratio. And the way that we do that is we say, okay, 84.5 times something gave us 67.6. It's going down. I'm expecting my number to be less than 1. So rebound ratio should be less than 1. And 84 times something gives me 67.6. That's a ratio of 67.6 to 84.5. Put that into a calculator. So 67.6 divided by 84.5. I get 80%, or 0.8. 0.8, which is good because it's less than 1. What height did he drop the ball? This is a little bit tricky. So the number of bounces would be 0, and I'd be looking up here. And if to go from 84.5, it's multiplying by 0.8, and then to go from the next one, it's multiplying by 0.8. How would I go backwards? So if it's multiplying to go down, then it must be dividing to go backwards. So divide by 0.8. And so 84.5 divided by 0.8 gives me 105.625. I'm going to do it again. Divide by 0.8. And so divide that last number by 0.08, or 0.8, excuse me, and I get 132.031. And I'm going to only go out 3 decimal places. So his starting height, what height did he drop the ball? Starting height. The starting height was 132.031. Okay, and my equation, and if we go back, we have to think, okay, we have this equation y equals a times b to the power of x, where a is our starting point and b is our multiplier. Oh, it looks like our multiplier is 0.8 and our starting point is 132. So we're going to just write that out. Y equals 132 times 0.8 to the power of x. And this is our equation. If I'm going to explain the equation, this is my starting point, and this is my rebound ratio. Okay, we're going to move on. A major technology company, Expogrow, is growing incredibly fast. The latest prospectus, a report on the company, said that so far the number of employees Y could be found with the equation Y equals 3 times 4 to the power of X, where X represents the number of years since the company was founded. How many people founded the company? How can the growth of this company be described? Okay, so our equation y equals 3 times 4 to the power of x. We're going to first see how many people founded the company. Well, we know that in an equation, the 3 is the starting point, and we know that the thing in time inside the parentheses is the multiplier, or the growth rate, growth or decay rate. And because the number inside the growth rate is bigger than 1, in this case the growth rate is 4, since it's bigger than 1, we know that it's growing. So for this one, this is the growth of this company. So we know that how many people founded the company? 3 people founded the company because it's our starting point. And based on the growth rate, the company grows. The company grows by a factor of 4. Grows by 4 times each year. Each year. So this year they have 3 employees. Next year, so year 2, at the end of year 1, they're going to have 3 times 4. So they're going to have 12 people in their company. And the end of the next year, it's going to be 4 times as many as the previous year. So it grows by a factor of 4. You could make a table of values and see on year 0, year 1, year 2, how much it grows by. But it grows by a factor of 4, or times the number of employees by 4 each year that goes by, which is a really fast growing company. Can you imagine how many people there would be at the end of 10 years, maybe? It grows really fast. All right, so a computer virus is affecting the technology center in such a way that a certain portion of the virus-free computers is infected. The number of virus-free computers is recorded in the table down below here. How many computers are infected in the technology center, and what portion of the virus-free computers is infected each day? How many computers will remain virus-free at the end of the third day? So we're going to think about 3 here. Justify your answer. So we're going from a table into a situation, and we're trying to describe the different pieces of this. So how many computers are in the technology center? So we know that on day 0, before the virus hit, there were 27. So there's 27 computers total. What portion of the virus-free computers are affected each day? So that must mean the rate at which the uninfected computers goes down. So how much is it? 27 to 18. So that's going to be the ratio 18 over 27. I'm going to put that into a calculator to see 18 divided by 27 is 2/3 of the computers are infected or remain uninfected. Let's say remain uninfected each day. So what portion of the virus-free computers is infected each day? So if 2/3 remain uninfected, that means 1/3 is being infected. So 1/3 is being infected each day. How many computers will remain virus-free at the end of the third day? So it looks like they're multiplying by 2/3, multiplying by 2/3. So this pattern of exponential growth seems to be multiplying by 2/3. So 12 multiplied by 2/3 will give me 8 computers are remaining uninfected on the third day. So 8 computers uninfected on day 3. And the justification here is that it's an exponential decay of uninfected computers, in that they're growing down by a factor of 2/3 each day. All right, we're going to move on to the fourth 720D. As part of the major scandal, it was discovered that several statements in the prospectus, or the report, from Part B were false. If the company actually had 5 founders and doubles in size each year, what equation would have been printed in this report? Okay, so again, we're asked to write an equation, and exponential equations always come in the form of y equals a times b to the power of x, where the a is the start, and the b is the growth or decay. So in this, if the company actually had 5 founders, so 5 people starting it, we know it's going to be y equals 5 times, and doubles in size. Doubles is a factor of times 2. Doubles in size, you take 2 to the power of x. And so we could rewrite it like that. And this equation would tell us how many people are in the company on any year x, where x is the year after start, because it starts on year 0, obviously. All right, we're going to move on to the next question. Most of the exponential equations have used in this chapter have been in the form of y equals a times b to the x. That's what we were just talking about. What does a represent, and what does b represent? Well, a is the start, and b is the growth factor, or decay factor. And when the b is bigger than 1, it's growing, and when b is less than 1, it's decaying, and when b equals 1, it's flat, there's no change. How can you identify a by looking at a table? How can you find it in a situation? Give an example for each representation. So a is the starting point. So if I had a table of values, x and y, it was always, when we did the computer problem, it was always this first part. So the a is always when the x value is 0. So from a table, if I look at a table, I'm looking for the 0 in the x column. How can I find it in this situation? For a situation, so for a situation, it's always the starting point. So a situation, it's always the starting point. And if I were to give an example of that, if I were to give an example of the starting point for a situation, maybe I would, I could think about how much money I owe for a loan. So the money owed for a loan to start. Money owed for a loan to start. Or I could think about the people at a company at the beginning. People at company at the beginning. Sorry, my handwriting is terrible. All right, so I think we've satisfactorily answered the second question, which is looking at A. How could you determine the B in each situation? Use arrows or colors to add your ideas about B in the examples you created in the previous part. So B is the growth rate. And so I guess in the previous problem, 27, the times 2/3 was the times 2/3 portion was the B value, and the starting point was the 27, which was the 0 value. So B for this representation is the thing that I'm multiplying by, and for the if I'm thinking about B in a situation, if A is the money I owed at the start, the B is the interest rate. And if I'm thinking about the people at a company at the beginning, the B is the people growing each year, the factor of people growing each year, factor of people growing each year. Okay, so for both of these situations, the idea is that A is in the red and B is in the blue, to discriminate between what is the meaning of A and B for a situation. So then if I know this for a situation, I can really think about y equals A times B to the power of x, this equation we have, as this kind of template for any kind of additional exponential functions. All right, and this is our last question. So how can you sketch the graph of an exponential function directly from its equation without making a table first? Discuss with your team, then make a reasonable sketch of the graph of y equals 7 times 2 to the power of x on your paper. So my hope is that by this point in time, you know that 7 is the starting point and 2 is the growth factor, so that if I were to start graphing a sketch of this, where I have x and y and 7, 14, 21, 7 times 28, I got 35. So I'm going by sevens on, and I'm going to go by 0, 1, 2, 3. I know my starting point is at 7, and so that should be an automatic give me. That my starting point is at 7, and then I double each time. So after x increases by 1, it's going to double to be 14, and then double to be 28. 28. Oh, that's so wrong. That should be 35 if I'm going by fives. And then doubling again will grow just exponentially to all the way up to 28 times 2, because it's doubling each time. And so a reasonable sketch of this is that, hey, like if I went into the negative world, it would keep going down, and if I kept going to the positive x values, it would keep increasing. And this is just a generic, it's a reasonable sketch. Is it perfect? Absolutely not. Is it close to perfect? Kind of, but it's not perfect. It will never be perfect. So hopefully in seeing these few problems that you can feel successful in doing your homework. Your homework being 24 and 25, I'm really hopeful that you have the content knowledge to be able to access those two problems, and we'll go over problems when I come back and see you on Thursday. Hope this was a successful class and that you could review your homework. Let me know if you have any questions. My email is rgermani@fwps.org, or you can always check out my website, mr.germanis.org.